Guys, again, I had a whole video created on the number e, and apparently the volume didn't carry through. So we are going to try again with the number e. Um, Sounds kind of weird already, doesn't it? E is a letter, but in fact, it is a number, much like pi is a number as well. So first, we're going to decide what does e represent. Well, e, we're going to talk about this stuff a little bit later. Um, E is a limit. Actually, the limit is something that, again, we haven't talked about. We will get into more next chapter, but it's a huge concept in calculus. And E is a limit. A limit is basically, you can think of it in terms almost like an asymptote. It's a number that you approach, but can't necessarily actually get to. So that's where E comes in. And E is the limit as n approaches infinity. That's the terminology here of 1 plus 1 over n to the nth power. So what that means, let's let n equal, and we'll say n equals 1. Well, then we have 1 plus 1 to the first power. That's 2. Let n equal 2. We get 1 plus a half squared. Well, that's 2 1/4 or 9/4. So on and so forth. 1 plus a third, and we're going to cube that. So that'd be what, 64 over 27, I believe we're looking at there. 64 divided by 27, which is 2.37. 2.37, so on and so forth. Let's look at this a little differently now. Y equals 1 plus 1 over n to the n. And I'm going to go to my table setup and make sure I'm on the ask feature, and I am, ask, and I'll go to my table itself, and I'm going to plug in different values for x, 1, 10, 100, 1,000. So in other words, as n is approaching infinity, it's getting larger and larger, right? The limit as n approaches infinity. N increases, what happens to the value of the function? Well, eventually it gets this value right here when n is 1 times 10 to the 6th. All right, that's 1 million. When n is 1 million, 1 plus 1 over 1 million to the 1 millionth power. And it comes out to 2.71828046923. Dot, dot, dot. Goes on and on forever. Bottom line, that is what E is defined as. There's that value right there. And if you look on your calculator, second natural log, whoops, let me quit out of here. Second natural log gives you E, and raise it to the first power, and there's our 2.718 we were just referring to. Okay, so we showed it two different ways by using the graphing calculator, using a table. There's a value right there, and here it is, the actual value of E as best the calculator can approximate it. Remember, we only went up to 1 million here. If I get up to 100 billion, a trillion, a googolplex, right, this number down here will look more like this number. All right, that is the number E. I apologize, you got some stuff disappearing here, so we'll bring that back, forward and backwards, and all our ones are back there now. So things we need to talk about that relate to the number E, we're building up on that. We'll start with some basic interest problems, and remember our equations. If we're talking about simple interest, that's something that's compounded one time per year or one time per cycle. Where your simple interest, your amount, which of course is dependent upon time, is equal to the principal, how much you invested initially, times 1 plus your rate raised to the t. Okay, this is your rate as a decimal, rate as decimal, decimal, and this is your time. And of course, P is your principal, your original investment. Principal, original investment, or if you're purchasing a car, your purchase price. So that's simple interest. Okay, just like we did before, if you have 6% interest, your multiplier is 1.06. That's 1 plus 0.06. That's a regular equation. Okay, this is the normal exponential equation. Normal exponential model. And then you get into some real life applications when you're talking about compound interest. That's, you know, you go to a bank and you get a monthly statement. That's because they compound your interest. More often, they typically do it on a daily basis. CDs, money markets can be done on a monthly basis as well. So compound interest is your original investment times 1 plus R over N to the NT. Again, R, that's your normal, your rate. This is the number of compounds. Number of compounds. I'll explain that in a minute. T again is your time. Typically in years. Years usually. Some of these A's are disappearing. And again, your principal right here, your initial amount. Principal. So what happens here? Let's say we have an APR, annual percentage rate of 12%, and you're compounded monthly. That means every month when they calculate your interest, you are going to get 1% per month. 12% divided by 12, compounded monthly. Okay? If I did 12% divided by 4, that would be quarterly. Right? There's going to be 4 quarters in a year. Every 3 months, they'll figure out your interest. You'll get 3% each time. If I do 12% divided by 365, that's daily. Right? These are your N values. N equals 12. N equals 365. N equals 4. And if you think about it, it's kind of intuitive that if you're getting interest every month, through the course of a year, you're going to be getting interest, calculating interest 12 times in a year. So if we look at our equation up here, if you're getting interest 12 times per year, that's why it's NT. In 2 years, you're going to do it 12 times 2. You're going to get 24 compounds throughout the 2 years. If you're doing it quarterly, okay, quarterly, that's 4 compounds a year, or 8 every 2 years, or 12 every 3. So that's why it's to the NT. Okay, your exponent is higher, but your multiplier is lower because it was R divided by N. Your 12% is really a 1% each month. So let's look at a couple examples of this. You invest, let's say, $5,000 at 12% interest. All right, and then that is your APR, annual percentage rate, remember? And let's say you are compounding. Well, you know what? Let's start off with simple interest. Let's say this is simple interest. How much do you have after 2 years? And this is going to be simple. So we will do our amount after 2 years is 5,000 times, well, 12%, that means I'm at 1.12, right? 1 plus R to the second power. All right, so 5,000 times 1.12 to the second. Oops, I missed something there. To the second equals $6,272. Pretty good. Okay, that's your interest right there after your money after 2 years. Now let's say we're doing compounded monthly. Compounded monthly. So it should make sense that this is going to be a little bit higher because you're getting interest on your interest. You're compounding it more. So we have 5,000 times 1 plus 0.12, my percentage rate, divided by 12 months, raised to the 12 times 2. 2 years, 12 months. So if I simplify this, just to make it easier to plug into my calculator, I'm going to get 1.01 raised to the 24th. So basically the same equation, but instead of 1.12, I have 1.01, and that is raised to the 24th power to 4, and we get 63, 48, 68. 63, 48, was that 68, I believe, was the change? 67 cents was the change. So a little bit more than before. Okay, so that's how compounding changes. You're going to get more money. And of course, if I change this to bi-weekly, you do 24 compounds, or 26 compounds in a year, right? Once every 2 weeks, and there's 52 weeks in a year, so that'd be 26 times. The other piece we have here is something called continuous compounding. That's where the number E comes in. Continuous compounding means essentially it's getting compounded all the time. Obviously, you can't compound all the time because you ask for a quote, and they say, oh, okay, you owe us $5,000 to pay off your interest. Oh, sorry, it's 5,002 now. Oh, 5,004, 5,007. You can never actually pay it off if it's continuously compounding. So a little unrealistic, but most of them are done. Population is done on a continuous model. Population growth, how people are born and how they pass away, the amount of people in the world, the amount of rabbits, the amount of any kind of population, dust mites, they grow on what's considered a continuous model, and that again deals with all similar letters. But this is what I like to call the shampoo equation. How many of you guys use PERT plus? I for one do use PERT plus. Mostly because of the mathematical background of PERT with the E in it and everything. So it's a very, very clean equation. Did you see that little pun there? Clean equation, shampoo? Yeah, anyway. So let's take this problem. Say we're doing it for the same 2 years at a continuous rate. 5,000 E. My rate is, where are we at here? 12%, so 0.12. And my time is 2 years. So we go to our handy dandy nifty TI-84 calculator. I type in 5,000 and second, natural log using the E, and I'm going to the 0.12 times 2, or 0.24. And my number, notice, is slightly higher. I get about $8 more than before, 63.56.25. 63.56.25. 63.56.25. And since we're compounding, quote unquote, all the time, it should make sense I'm doing more compounds than once a month. So this value should be higher. So those are our main guys for today with the number E. This is where the number E comes into play with the continuous model. We also have our compound interest, all right? And then we have our simple interest here as well. And all that stuff we got going on here. Nice applications. So we'll go over some things about how to find a mortgage. I'll give you a nice little equation for that. By little, I mean a really big equation for that. And different techniques and things we'll get into with that. Hope you enjoyed the video on the number E and its uses, especially in the nice shampoo equation. Nice to have you today. We'll catch up later.